Hello and good morning, everyone. And thank you for joining me for the continuation of Module 4. And today we are going to be talking about network analysis. This morning is the first of 3 sessions we will have. So some of you may be relieved it's going to be quite a gentle introduction to the topic today, not too taxing, so just really an overview of what it's all about, some of the terminology we use, as well as actually getting your hands on some data, and you'll be doing some exploratory data analysis in your groups, which is kind of going to rely on you guys actually starting to think about how you'd interrogate data at a very high level to just get some basic insights. And then we'll be moving on, and you'll actually get to build a network graph yourselves later today. And then next week, we'll kind of get into the advanced sessions, which are going to be really good. And you'll actually be creating web-based GUIs of, networks that you can move around and change the different parameters. So it does get quite interesting quite quickly. But anyway, enough about that. Today, we are going to, if I can get the slide to progress. There we go. So our learning objectives for today, as you may expect, to understand what a network graph is and how it is constructed. Then you're going to be able to, as I say, transform raw data into a suitable format so it can be used for network analysis. And then we'll be creating a simple graph ourselves in Python using a library called NetworkX. So in the chat, can I just make sure that everyone can see all of the screens, no black boxes on it at all anywhere? But here, nothing, I'll assume it's all okay. Cool, thank you. And so what is a network? Well, network graphs are used to study large and complex systems. They are a way that you can have lots of information that if you looked at it in a list, it would just be overwhelming for the brain to kind of take in. But it is a way to visualize things that is going to make it comprehensible at a relatively easy level. And you can kind of pile and pile more information in to make it more intuitive and kind of to be able to convey more information in an easy to understand format for the reader or the viewer. And really, it helps us visualize relationships and interactions in, as I say, a very intuitive way. And it also allows us to represent abstract concepts in a more concrete way. And you'll see, I mean, I'm not sure if anyone has seen one of these before, but when you start seeing the type of raw data that goes into creating the final product, you'll see what I mean, that it's much more intuitive, and it's a way that a lot of people could understand, regardless if they knew a lot about the topic in question. And, it was kind of it sort of really came into the foreground, or it was really used by Euler in the 1930s, and he was using it for logistical problems. Again, it had to have a very easy way to overview complex information. But it really has its roots back in medieval days. I can't remember the exact year. We'll talk about it next week with the 7 bridges of Königsberg, which, as I say, we'll talk about more. But essentially, they wanted to find, was it possible to navigate around this town that you can see at the bottom right with only passing over each bridge once? And we'll work out the answer to that later. Cool. So some examples of where you can use network graphs, and they would include, and obviously top of the list, my favorite, airline networks. And with these, the vertices, so vertices and nodes, these are some of the terminology that you're going to get to learn over the next 3 sessions, would be your airports. So then the nodes, these would be the dots, if you like, on the graph. And then you've got your edges, and these are the lines that move between the dots. And in this case, that would be actual aircraft or routes operated by airlines. And then you can start adding in more information to increase the richness or the dimensionality of the graphs. For example, with the vertex or the nodes, confusing that they have two different names, you think about, what is the total footfall, like how many passengers are physically on each aircraft, and the terminals, the number of passengers passing through the airport, the number of terminals at the airport itself, so on and so forth. And with the airlines or the edges, the lines that move between them, you can think about, the frequency operated, number of passengers actually carried versus capacity, aircraft type, so on and so forth. But then to kind of take it outside of my favorite topic, you can also use it for banking networks. And here, your nodes or your vertices, the dots will be your account holders, so the individuals, so, University of Exeter, Dan Chalk, Elliot Coyne, all of our colleagues. And then you'd have transactions. So obviously, they would hopefully the university pay us once a month, and then we go and spend our money elsewhere, and money will be bouncing around everywhere between vendors and what have you. Then obviously quite an obvious one would be social networks. And, again, the nodes or the vertices are the individual users. And they start to look at the interactions between them. And, this is how things like suggested friends may come up if you use Facebook, because they look at, well, you're connected to all these other people who they seem to know this person, so possibly you do as well. So it's quite an interesting way, and obviously it makes it quite obvious, and something a lot of us will see in our daily lives if we are social media users. Then bringing it into a health perspective, this has come from a US site, so they talk about the physician network, and so your vertices or your nodes being the doctors, and then the edges are the patients. Possibly more relevant in the US, where someone may have more than one GP. Same in other countries as well. When you're paying for it, you get to choose where you go. And so they might have one doctor for the diabetes, one doctor for the pain, so on and so forth. And so you can start to build a network of where these patients are moving around. But here in the UK, probably more relevant if you think about, an example we'll see shortly would be a mental health service. So your patients coming in, they're referred to this service, then maybe that's referred to that service, or they may be admitted, and then you can kind of follow through, the flow of patients, and it's really, really interesting to put so much information in something that's so easy to understand. And then back to, what Euler was using in the 1930s, and, supply chain network. And here you could be thinking about your different warehouses. So think about Amazon. They've got distribution centers located all over the country, and then trucks. So they've got to send stock between one distribution center and another. And then ultimately they've got to put it out into the community when they're actually delivering to our households. So just to give you some examples of what a network graph looks like, here we've got an example, and this is based on Twitter handles, and you can see each of the dots. These are the nodes, aka vertices. These are the different handles of users. But then these lines will be retweets, or if they're sharing the content of that user, excuse me. And so you can see that they're all interconnected. One example, if you think, what's the old saying? You're connected to anyone in the world by 6 degrees of separation. Well, this kind of shows you in the Twitter ecosystem how these people may be connected. And I think that possibly George Galloway was on I'm a Celebrity, Get Me Out of Here when this was created. And so you can see he's probably got one of the biggest dots going, possibly even bigger than CNBC News in the US. Then we've actually got an example here, which was a previous HSMA project. I'm afraid I don't know an awful lot about the project, but ultimately they were looking at the relationship between offenders and victims. So obviously in the police setting, as opposed to health. And, again, lots of interesting insights that you can kind of gather from these types of analysis. And then there are also interactive examples. And so my colleague, Sean Manzi, from whom these slides are adapted, he has created 2 example ones, which I'll show you now. One of them, a bit of fun, is about Game of Thrones. And then the other one is just related to some health data. So if we jump into here, and just to show you the Game of Thrones one. So probably a tiny bit more advanced than we'll get to, but ultimately this is, the web-based dash site escape library that allows you to kind of become interactive. So you can click on what season you're interested in. then you can start seeing the relationships between the different characters in the series. And I'm just using my mouse wheel here so I can scroll in and out. But then let's say I wanted to look at season 4, and then it renders that on the screen. And then again, you can zoom in and out and get more information from it. So quite intuitive, and it makes it a bit more interesting for the end user if they get to have a play themselves. And then just to show you this Wilfred data set, again, possibly slightly less interactive, but you can click on the nodes, move them around. And again, I think this was looking at review of systematic journal article reviews from memory. So as you can see, lots of different examples, and hopefully you could start to think of how this could be relevant in your place of work. So just to give you a bit more of an example with the health lens context, obviously, if we think about the whole structure of what we have on the right there, the graph is really representing a service structure. So the nodes or the vertices, these are the dots, these are the services. And so in this example, this is a mental health example from the Exeter area. And you can see, you've got Denderfield, Exeter, Allied Mental Health Partners team, Devon Liaison and Diversion team, Exeter Crisis Resolution and Housing team. And then the edge or the lines that move between them are the patient movements. So if we look at here, this is what we will call a directed graph, and that is because there is an arrow. So we know lots of patients move from Denderfield into this Exeter AMHP. Then we can see quite a few will go down to the liaison and diversion team. And then most of those are referred back to the CRHT, but some of them could go on to forensics. And so you can start to see the flow of the patients through the different system. And as I say, the edge weight is to do with the number of patients that are moving through. So think of it as a pipe. How wide does that pipe need to be to accommodate the number of patients? And you can also start putting more information into the node attributes just to help understanding. So, the different colors of the nodes will refer to a particular feature. And as I said, the arrows are representing the direction of travel. And then the size and color, as I say, we can embed different attributes into those, so you're kind of layering on more and more information. So what is a network graph? It is a graph-based representation of a system. It's based on pairwise relationships between entities. So as you remember from the previous slide, we had Denderfield going to Exeter AMPH. And then obviously they can be one, you might just want to think holistically, how many patients move between the two services, or you may want to know the direction of travel. And then do they just go in one direction, or could they possibly be referred back up to the original place? And also it allows you to quantitatively encode the properties of the system within the network structure. And we'll talk more about that later. And also, if you're thinking, what is a graph? Lots of people think of a graph like I did when I learned about this topic, or isn't it, a bar chart or a scatter plot? What we're talking about here is representing this information in either Euclidean space or Cartesian coordinate systems. So the slides do have those are clickable links, just if you want to read some more information about them from Wikipedia. But essentially, they're just, an X and a Y axis if you're doing it in 2 dimensions, and then dots on those axes. And so some of the things that you might include into the data that you could encode within the visualization to the nodes, things like the length of stay, how big the waiting lists are, the centrality of the nodes. Now, these are one of the metrics we'll be talking about next week, and the number of nearest neighbors, the number of connections the particular node has, and so on and so forth. But I appreciate I've been throwing a lot of terminology around. And so now just to kind of circle back and make sure that everyone is comfortable with this. As I say, We have our nodes or our vertices. I'll try and refer to them as nodes, but it's good to know if you're ever reading any literature, they're talking about vertices, they are used interchangeably. And it's all come from maths. And so you can see the red line pointing to dot V1, but V1 through V5 are all nodes. You then have your edges, which are the lines that connect the different nodes. So a standard graph would just be unordered pairs of nodes. So it doesn't matter the direction of travel, we just know there's a connection between one and the other. You've then got a directed graph, and that is where things are ordered. So you follow the sequence, patients start here, they get diverted there, some will go this way, some will go that way. And an example of that would be someone who presents to an emergency department, and then they go on to be referred to orthopedics. You've then got your edge weight. And so this is the thickness of the line that runs between the nodes. And as I've said, times for this can be number of patients, number of passengers, just so you get an idea of relativity, how much thicker is this line compared to the other one. And that just shows kind of the flow through in that particular direction. And as I mentioned earlier, you can then start, coloring the nodes with depending on different attributes that you want to kind of add in. So some other things to point out, we've got our parallel edges. And so in this example, we can see V4 and V5. They're parallel because the lines run, one goes V4 to V5 and one goes V5 to V4. So that's, as I say, parallel. You've got loops, or otherwise known as self loops. And that's the example here. That would be V5. And that's when a patient, or someone is re-referred into a service. They don't go anywhere else. They just, they go and come back to the same place. We have our adjacent nodes, and this is where you will have, they will stem from a distinct or a single node, but they're kind of, they're next to each other, going to different destination nodes, which that has their own terminology as well. And then you've got the adjacent nodes, two nodes that are next to each other and connected via an edge. So something else I haven't talked about yet is also we have sources and targets. And again, this is where we worry about directed graphs. So, the source, the origin would be V1, the target or the destination would be V2. We'll talk about that. And so the data that you need to build a network graph, there's some things that are mandatory, and then there's some things are optional, depending on how much information we're going to be layering onto it all. And so, for the node list, this list of nodes, we usually have a numerical ID. So this is just a unique identifier, like an index. You then have your label, which is usually a text-based, text description of what that node is. You've then got your edge list, and the edge list will say what is the source and what is the target for each line that's created between the nodes, remembering that it's probably using the index number that you've already referenced. And then you can start adding on any number of attributes on top of that, for example, the weight or, the number of people who are traveling through that. And then obviously you can have self loops, and they are represented in these as having a source and target being the same value. That's how you'd generate your self loop. So I appreciate a bit of a whistle-stop tour there, move pretty quickly through that. But just to kind of get you to say hello to each other, have all the nice formalities, we've got our first exercise. And with this, I have given you some data, and I'm just going to move into the Jupyter Notebook. So data one, literally, I haven't really given you much to go with. I have given you the library import, so just pandas. You're then going to import some mystery data that I've sourced off the interweb for you. And it's really up to you guys. I am going to allow actually 35 minutes for this task instead of 30, but I would like you to work in your peer support groups, have a look at it, open it, and then start drawing some insights and conclusions. And then when we come back together at 10:25, I just will pick a group or two, just so you can tell me what is the data, tell me some things about it that would be relevant or pertinent to a network graph. So before I do that, just checking, has anyone got any questions? And just to remind you, you can run this locally. I gave you the environment file in the Binder subdirectory, or it is also available on Binder Hub. The link is in Slack, so hopefully that will work for everyone. All right then, so if no one's got any questions, I shall pause the recording and open the breakout rooms. Hi everyone, and welcome back. I'm just making sure everyone's back in the room because it looks like the rooms are still open. So as I said to a couple of the groups, this exercise was not, it wasn't a trick or anything. I just thought it would be a good icebreaker for a Tuesday morning on a new topic, just to be given a CSV file that you knew nothing about, and just pull out any insights at all. Even if you could just tell me what the data was, that would be something. So don't worry, it doesn't have to be highly in depth. It's just, as I say, just something to get you thinking kind of off the guardrails of having a completely structured exercise. So with that in mind, I shall share my screen, and I'm afraid I am going to use the Dan's wheel to pick a group. Let's see who our unwilling volunteers are going to be. So I do hope you remember what room number you're in, but if Atari ST, anyone from your group, happy to just chime in and just give us a couple of facts that you've discovered through looking at the data.
Yeah, I can go over mine.
Cool.
So I went through and looked at when the first flight was and when the last one was, and all the flights are in 2022. Looked like in the first 7 months, and there were just over 94,000 flights, with some flights having 0 airtime, and the average airtime being just over 3,000 minutes, I assume. And then, yeah, then there were some other things, but.
Cool, fantastic. So, I mean, obviously, you discovered it was, aircraft movements between US airports. Fantastic. Look, I won't dwell on it though, but hopefully everyone had an opportunity to have a play around with pandas and was able to kind of draw some kind of insights, as I say, even if just source and targets. But it gives you a flavor how this type of information can be used for these purposes. So to carry on with the lecture, so now you've seen, you get data from scratch and then kind of deciding how that could be used for network analysis. Next, I'm going to be talking to you about how we would transform data, and we're going to be doing this, with the health sphere as usual, on patient level data. And so as this part of this process, we are, and I'm just going to open the file to show you, we have got some data already loaded. Yeah, here we go. So this is the data file that I'm referring to on the slide, PD data HSMA 2020 CSV. We can see, quite a bit of information in there. But ultimately, we've got a client ID, so a unique reference referring to a single person, a referral date into a service, and a discharge date, so the date they left the service, the source where the referral came from. Then we've got the team, the specialty, an ICD-10 disease classification code, the description of what that is, settings, so on and so forth. So fair bit of information there. And let's go back to the slides. What we need to do with this when we want to transform it so we're able to use it for our network graphs is we need to clean the data, and involved in that you've got to make sure you've got consistency with the categories. You need to make sure that there's no negative dates or erroneous white spaces, because Ward 1 and ward 1 with a space at the end, even though visually they look the same, as you'll know with data integrity, that could be picked up as 2 distinct different wards, even though they are physically just one. And then obviously consistency, things like spelling, which we'll touch on. We then need to order the data. And what we'll do, we'll first of all order it by patient. So all the patients will be segmented together, and then by date. And by doing that, we can see how services would sequentially be used, even though they may use some services simultaneously. You kind of get an idea from chronological start to finish, where they start from and to. This information will then be used to create something called an adjacency matrix, which it's going to be easier if I just show you on the subsequent slides. But essentially what we're going to do is then iterate over this interaction or adjacency matrix to create our edge list, and in that picking up the source, the target, and the weight. And then we've got to consider, the unique instances or services that are going to form the nodes. And that really depends on the resolution of the data and how you want to subset it. So to consider that some more, the things that we really need to consider when we're cleaning this type of data are, the inconsistencies. So use of capitalization, uppercase, lowercase. Probably less of an issue if you're just using numerical IDs, but if anything else with text labels, it is a problem. There's also spelling mistakes if for some reason there was a manual entry field as opposed to a predefined drop down, and you obviously want to avoid inadvertent replication. Example I gave before, ward 1 space, 2 different things. My pet hate in life is people spelling my name wrong. My name has 2 L's and 2 T's, but no matter how many times I say it, the emails always say 1 T, and it's it's tough. But again, silly things like that could end up causing the graph to not actually accurately reflect what reality is. We've already talked about the erroneous white spacing, so leading, trailing, and then within the text itself. You could have incorrect date entries reversed between US and UK, day, month, day, or they could just be missing altogether. And then holistically, you could have missing data for a whole number of reasons. And so these are the things that will need to be ironed out before you actually start to try and create your adjacency matrix. So as I say, we wanted to order our data, and you do this to create the adjacency matrix and then iterate over it, and you actually go row by row. And that's how you'll go on and form this adjacency matrix, which we've heard so much about. But essentially, each row would be the ID of the source. Each column would be the ID of the target. And you're basically going along. And if you can see in this example, we can see that there is an edge going from ID 2 to ID 1. And there's a weight of 1. Where if we look at this one, for example, it's going from ID 5 to, again, ID 5, and there's 9 occurrences of that in total, and that's where you start to get your weights. Obviously, you'd start the matrix when it's first created full of zeros. You know what your sources are, you know what your targets are, and NP numpy zeros, create that in, and then start going along and counting up the number of occurrences for each pairwise set of nodes that you have. The problem with this is that it can, as you can imagine, take a lot of computational processing power and also potentially storage, depending on how big the system is that you are trying to model. And then once we have that, we then start to be able to create our node list. So remember, the nodes are the dots. I'm sorry to keep repeating it, but we just need to get it drilled in. These can otherwise be known as vertices. And we can see here, they've got their own unique ID in this gray column here. Then they have a text label. So these are the mandatory. You've got to have an ID, which is usually numerical, and then a label. But then we've also put some other attributes on to that node. So we can see the mean length of stay for the, for area 10 is 23 days. You've got the median length of stay, and then you also got the setting that it is. So is it community, whatever, so on and so forth. And so you can have as many attributes as you want. It could be tied onto that. You've then got your edges, and these are, remember, the lines that connect the nodes. And again, the things that you must have here are a source and a target, because you need to know kind of what pair they're going through. And obviously, if it's a directed graph, and that's where you know, the flow in one direction may be different to that of another, you'd have to say, you know, in this example, from 37 to 0, and the weight is 1. But then you'd also need to consider what is 0 to 37. You know, is there any movement at all between in the opposite direction? Because we are interested in that direction of travel. So this takes us on to the next exercise. Now, it's an interesting one. The code has all been provided for you. However, there are 4 main steps as described in the earlier slides. And within each of those steps, there are 2 sub-steps. So I'll show you what I mean, just to make sure that no one gets overly confused. But essentially, the part that's static, because we're very nice, I'm going to give you the imports and give you the data. But with each of these 8 boxes, they are currently jumbled up. They are not in the right order. They're not occurring in the correct sequence. So what you need to do is use the arrows available in Jupyter, so you can change the sequence of them. So I'm highlighting a particular cell by clicking to the left of the active area, and then I'm using these up and down arrows to move them into the right sequence. So what I'd like you to do for your next exercise, for which I will be allowing 35 minutes, is to kind of have a look at the high-level overview, then read through each of the different steps, put them into the right order, but also if you need to create some additional cells. So to do that, you can, if I select an active cell, hit A for above or B for below, and start, you know, use print statements, find out what each step is doing and make sure you understand it. And then ultimately you're going to create, or this will output 2 CSV files, which we're going to need for the next exercise. So this is going to spit out a node list and an edge list, because in the next exercise, we're actually going to create a network graph. So just making sure everyone is comfortable with those steps, and they're comfortable with the idea of shuffling the cells in Jupyter Notebook and also inserting new rows above and below. Cool. No news is good news. So again, I'll open the breakout rooms, and if it's okay, if we can remember the number you were in, and then we'll reconvene at 11:15, if that's okay. Cool. Hi, everyone, and welcome back. I hope you were all able to work your way through that without too many issues. Can I just quickly check that everyone can see Jupyter Notebook on my shared screen?
Yep.
Great, thank you. Zoom is not being my friend today. It's not coloring it green as you'd usually expect to see. So before I get going, I'll just make sure, did anyone have any issues at all? They weren't able to spit out the nodes and edge list? Great. and just checking that everyone ultimately was relatively comfortable with what all of the code was doing. I appreciate there may have been a few new things in there, like the dot replace methods and converting things to date time and picking out formats. But overall, between yourselves, did you kind of get to a point where you kind of knew roughly what was going on? I assume silence is golden, so that's great. So next, now we've got our nodes and our edge lists, I want to start talking about, well, how do we actually go about building a network graph with NetworkX? And so the high level process would be to read in the data, initialize the graph, so create the pane, the canvas on which we want to draw. We then need to format the node and the edge data, and then add the formatted data to the graph, and then ultimately plots the final graph once it's got all of those elements we're going to need in there. So when we do this with our, within the notebook we're about to use, obviously we're using it pandas read CSV to get in the data. We're initializing the graph object with NetworkX, which is imported as NX, and that's nx.graph with an uppercase G. We're formatting our nodes in edge lists, so we're creating, we're getting a list and dictionary, and we're creating that into a tuple. So you'll see how we do that. Then we're using the NetworkX add nodes from and add edges from, what we've already created. And then finally, we're going to draw the final layouts. So hopefully that makes sense at the very high level. Now, for task 3, rather than just simply put you into the groups to do it, I'm actually going to talk through what each of the stages does, because if anyone has looked at task 3, they'll see that actually just some snips of code have been replaced with some asterisks, or asterisks. And if you pay attention to this next section, it'll be a lot easier to complete task 3. Now, just bear with me. I just need to make sure I don't forget to cover anything. So, as I say, there's a file there, task 3, which you'll be working on in your peer support group shortly. But ultimately, the steps are as follows. We have our library and file imports. So NetworkX, which we're importing as an X, pandas as PD. And then someone's going to shoot me for lack of PEP 8 compliance, but there are some long lines here. So we're creating a new variable called nodes, and we're going to load into that the node list that we've just created. So you may need to, if you didn't adjust the output of task 2, you shouldn't need to modify anything. But obviously for nodes, you're going to be using the node list.csv that was created. And then for the edges, you're going to replace the asterisks with the edge list CSV, wherever that happens to be. Then the next stage will then be to create a brand new graph object, and that's going to be assigned to a variable uppercase G. So that'll be uppercase G equals nx.graph, open close parentheses. Then we're going to prepare the node. So there's a couple of stages in this process. So first of all, we are going to get the ID list. And so to get this, we are going to look at the data frame, the nodes data frame we instantiated in the previous step. And we're going to pull out a single column from that data frame, which will be the ID column. And then we're going to use the .toList function, and that's going to convert that data frame column into a list. We're then going to create a new data frame called labels, and that will be created from a data frame of the column label in the nodes variable. Then with the label dicts, as in the label dictionaries, we're going to convert this labels data frame to a dictionary with the 2 dicts. And that is going to give us we use the orient equals records. And when we do that, what that spits out, and hopefully you'll get to play with this yourselves. You've got dictionaries here, and so the key is always label, and then the value happens to be whatever it is. So that's what that will actually do. So feel free to have a little play around with that yourself, so you can see how it works, and there's the documentation for it as well. And then finally, we are going to create the node tuples. Now, if you remember from our data structures in module 1, a tuple is a data storage receptacle that once created can't be changed. So it's kind of set in stone, if you like. And to do that, we're going to use the zip function. And what that does is basically says, right, I'm going to pull the first element from ID list, and then the first element from label dix, then the second from ID list, second from there, so on and so forth. And it's going to make a tuple of R being the elements it's zipping through. So, you imagine a zipper on a coat zips together like that. Well, it's going to be the same. And again, it's going to put that into a list of tuples. So again, have a play with that and see what it looks like. And to give you an example of how the zip function works, I've created 3 different lists here: letters, numbers, and symbols. What I've done is said I for I in zip, letters, numbers, symbols. It basically goes, right, what's the first element in each? A1 hyphen, and then puts that into a tuple. Then it's got the second one, B2 star, so on and so forth. But again, have a little play around with that just so you understand exactly what it's creating. So don't be afraid to use print commands and what have you. And next we have got, we've got to prepare the edges and the weights. So we are going to use the source list. And again, from the edges data frame that we had, we've got to, you can see here, we've got the target and we're putting that into a list. Well, we want to do the same for the source. So we will replace these asterisks with the source to the list. We'll then get the weights, and that's using a data frame and pulling out the weights column in there. Weight, singular, sorry. Then similar to before, we're then going to transpose this weights data frame and to create the weight dicts object or variable, we will then use weights here and then convert it to dictionary and similar to the last edge of the orient record. So it will then have weight, the weight, so on and so forth. And then finally, we'll create our edge tuples. And again, with this one, we'll use our source list from here, and then we'll use our target list, and then we will get the weights, and so it'll zip through each first element of each 3, second element of each 3, so on and so forth. Once we've done that, we are then going to add our node tuples and edge tuples, which were the final steps of the last 2 slides, and we're going to add them to our graph object with the method .add nodes from and add edges from, respectively. Once that's done, we are then going to tell the computer, well, how do we want our nodes and edges to be laid out? Now, there are different types available, how it's visually represented on the screen, but the one we're going to use today is the Kamari Kwai layout. As I say, there are others, so it's worth having a look at the documentation. But essentially, what this will do, it kind of bunches them together, but also if for any reason they may be more disparate, so they'll kind of, it just lays them out in 3D rendering, just so it kind of is a bit more intuitive and based on some of the values within the data that we're using. And then obviously NetworkX kind of takes that information that you've said, well, how do we want it to be rendered? And it will utilize that when it physically plots it on the screen. And then, as I say, yeah, each element that's plotted on the screen has to have an XY coordinate, so it knows where to put it. And then this kind of ties that all together. Then the final stage is to actually draw the graph, as you'll remember from the previous one. And with this one, we are going to use NetworkX Draw, and we're going to put in the G, the uppercase G, with the map object we created in the previous slide. And we're also going to use pos equals pos. So you'll see in the previous slide, we created that here with the particular type of layout. Then again, feel free to play around with the node size, the with labels, Boolean, true, false, and then also the font size. And then, yeah, you will have a graph yourselves. Something to note, hopefully everyone used either the Binder environment that I provided, or they're using Binder Hub online. But different versions I've noticed of NetworkX and or Python leads to a slight difference in visualization. So if you see something different, don't be too concerned. It's just something to be aware of. So if anyone has had a look, you'll notice that we're using Python version 3.8 for this one. And that was just because I knew it was the most stable. And hopefully it all should work for the same environment should work for next week's when we start using Dash Saito for the interactive models. But we'll worry about that at a later date. Okay, so if that's okay, we're at 10:26 now. I am going to give everyone an hour to work on this next one. So we'll come back together at 12:25. So I'll open the breakout rooms. As I say, just work through the code. Hopefully, if you've listened to this part, you'll know what to paste in where. But again, don't be afraid to kind of rip it apart and see exactly what each step is doing, just to make sure that you are comfortable with it. And then after that, we'll be done for this morning. So hopefully you agree it's been a bit of a light start, but hopefully plenty to think about. So we're ready to get into the more advanced topics next week. Okay, then I shall just pause the recording. Hello, everyone, and welcome back. I appreciate I've called you back a little bit sooner than originally planned, but I think most people will probably be finished. So it's probably better just to give everyone a bit of a longer lunch break rather than just hang around for those extra 10 minutes. But hopefully everyone was able to reach the endpoint and they generated their graph, whether it be on the Binder Hub virtual environment online or on their local machine. So, today was, as I said, a bit of a slow intro, but the information will be coming thick and fast next week. So next week, we've got the 2 advanced sessions, 3 hours in the morning and 3 hours in the afternoon. And by the end of it, you'll be creating an interactive web-based representation of a graph. And it's going to have, the ability to put filters on and what have you. So it's pretty interesting. Sure. So I've just seen a question pop up just saying you're struggling to see the advantages of the graph. And I think if we go back to the example we had this morning, and let's see if I can just get it up on the slides, looking at how service users would use mental health programs in the community, it can be quite useful to start looking at the flow of patients through that service. And also identify, which services are used by which kind of groups of users, or if, for example, there may be a range of distinct and very different services, but you actually find that the same type of people or same numbers of people kind of move between them. And with something like that, you then may decide to consolidate those services into one geographic location, for example, or see if there's any synergy you can get by combining them, if it's always the same people or flow of people who use them. And sorry, just get this back. But as I say, next week, we'll be covering a lot more about the metrics, and you'll even have a go at uncovering the metrics yourselves, in which case it will kind of explain more about the usability, and I'll come back to you with more real-life examples that will hopefully illustrate this point to a greater extent. So the only thing that's left for me to say is that this afternoon, you'll have a 2-hour workshop. It's going to be by my colleague Alison and then her colleague Paul, and you're looking at discharge simulations with their project IPAX, which they'll explain the acronym. You will be using R, so hopefully everyone's got RStudio installed, but don't worry that you haven't seen it yet. I know that Simon will be talking to you in a couple of weeks about R, and you get everything you need to know there, but this is going to be very simplistic. Open the application, open a script file, run it. You don't need to worry too much. It's very much point and click, but it definitely a very good workshop that's been very well received previously. And so if everyone is okay with that, we'll leave it there, and then we will see each other this afternoon at 1:30. And as I say, Alison and Paul will be taking the charge there. Other than that, have a good, slightly longer lunch break, and I will see you then. Cheers.